We are next going to look at the alternating series test. This is a name you need to know. This is published and established, the alternating series test. Now, the alternating series test can be very formal, but what I want you to get out of it is observational, to be able to look at a series and determine, using this alternating series test, whether or not the series converges or diverges. I like to think of it as the glorified nth term test. If you remember, the nth term test, if it passes, then further investigation is required. But here, if it passes the nth term test, it actually converges as long as it's strictly alternating. So let's take a look at examples 1, 2, and 3. Example 1. The sum from 1 to infinity, negative 1 to the n minus 1 of 2n over 4n squared minus 3. Does this converge or diverge? Now, I am able to look at this right away and say it's going to converge. Why do I know it converges? Well, it passes the nth term test. If I'm treating this like the nth term, it passes the nth term test. That limit as n goes to infinity goes to 0. And at the same time, it strictly alternates, so that I know it's going to converge. So here's what we're going to write. We're going to state that an is this form here. Then I'm going to take the limit as n goes to infinity of the nth term without the alternating piece, and that is the limit as n goes to infinity of over 4n squared minus 3. That's going to obviously go to 0. Now, what we need to state is the following. We need to state the series is strictly alternating and decreasing in absolute value to 0. That's actually the buzz phrase that you want. You don't necessarily need to say this, you don't necessarily need to say that, but if you say this, the series is strictly alternating and decreasing in absolute value to 0, then we're going to say this series converges by the alternating series test. So that phrase in a star is the one thing you're going to need to remember to say. So therefore, the sum from 1 to infinity, negative 1 to the n minus 1 of an, which is the sum from 1 to infinity, negative 1 to the n minus 1 over 4n squared minus 3, converges by the alternating series test. Example 2, I see that this is strictly alternating. I'm going to discuss it through observation and then write some things. So I see this strictly alternating, but right away I see that the limit of the nth term is not going to 0. I need not go on any further. I see that it fails the nth term test. The limit as n goes to infinity of an equals the limit as n goes to infinity of 2n over 4n minus 3, and that limit is a half, which is not equal to 0, so this series will diverges as it fails the nth term test. So pretty neat. If the series strictly alternates, then we know right away whether it converges or diverges based on whether or not it passes or fails the nth term test. Example 3 is ultra important. We see that it strictly alternates, but we also have this 1 over n, which had a special name. If you remember, the sum from 1 to infinity of 1 over n had the special name the harmonic series. This one also has a special name. It's the alternating harmonic series. Let's see whether or not the alternating harmonic series converges or diverges, and then we're going to use it by name without having to do any work at all. So can you tell me what this does? The nth term is 1 over n. Then the limit as n goes to infinity of the nth term is the limit as n goes to infinity of 1 over n. That clearly goes to 0. So the series strictly alternates and decreases in absolute value to 0. So the alternating harmonic series converges. Now, this may cause some controversy and some confusion. We know that the sum from 1 to infinity of 1 over n is called the harmonic series, and the harmonic series diverges. But now we add this alternator that makes it strictly alternate, and then suddenly this series converges. This is not intuitively clear, and a lot of people have trouble understanding its concept, but mathematicians have come up with these definitions, and so we accept this ambiguous notion that it diverges one way and converges another way. And then this brings up a fairly difficult concept called absolutely convergent and conditionally convergent. Absolutely convergent or conditionally convergent? That's the question here. But before we answer that question, I need you to understand that there's a bottom line to this. Bottom line is that all of these series converge. They all converge by the alternating series test. Bottom line, they all converge. I don't like this word conditionally convergent. I didn't choose it. Conditionally convergent makes you say, well, maybe it converges, maybe it doesn't converge. If it conditionally converges or absolutely converges, bottom line, it converges. So these four series converge bottom line. Now, if I take the absolute value of all the terms to make it a positive term series, I am changing it. Then let's see what happens. Now that I've taken the absolute value, the first two series actually diverge. We have the harmonic and we have a p series where p is less than or equal to 1. So the first two now diverge and the second two still converge. So we come back over here and say this one is absolutely convergent, meaning if I take the absolute value, it still converges. If I take the absolute value of this, it still converges. Whereas in the first two, they are conditionally convergent, because when I take the absolute value, it then becomes a divergent series. So I don't really like the name. Conditionally makes me think that it's not convergent, but I want to repeat again that the bottom line, the thing that I'm really looking for, is you to tell me whether these series on the left converge or diverge, and they all, bottom line, converge.